Okay, we're here, we're live, we're ThinkTech. We're doing the SOEST show, the School of Ocean, Earth Science and Technology at Manoa. But guess what? We're really at Holmes Hall doing engineering today because this is a relationship. Okay, and our guests are Ohta. He's a professor of electrical engineering at the engineering school. And Joanthan Dang, who's a graduate student?
Yes.
A graduate student of engineering at the engineering school. Welcome to the show, you guys.
Glad to be here.
Yeah, thank you for having us.
So let's introduce yourselves and talk about how you got to be where you are. Okay, Aaron, where are you, and how did you get to be there?
Okay, well, I'm currently an associate professor of electrical engineering at Manoa. How I got to be here, it depends on how far back you want to go, but I'm a graduate of Kalani High School. Actually, Joanthan Dang also happens to be a graduate of Kalani High School, but a few years apart. And I went to Manoa for my undergraduate degree. I then went to the mainland for my master's and PhD, and I was lucky enough to be rehired at the University of Hawaii at Manoa once I graduated.
Great story. So you came back.
Came back, yeah.
Where did you go to school for your PhD?
Berkeley.
Berkeley, that's
Yes.
a really, really good school.
It was fun there. Yes.
You had opportunities all over the country, and you came back to Hawaii.
Well, I wanted to come back here eventually. I was considering working in California for a bit, but one of actually the current professors in the electrical engineering department that was one of my teachers told me that he knew that I was getting close to graduating, and he said, well, there's some openings in the department, why don't you try applying? And so I took that opportunity, and I was lucky enough to get in.
All right, excellent. Why did you go to engineering in the first place?
Why did I go to engineering in the first place? Well, actually, as a high school student, I was a little fuzzy on what engineering actually was. Hopefully, high school students now, and maybe John can speak to this, have a little bit better idea, especially with all the robotics projects that are going on at the high school and sometimes middle school level in Hawaii. But anyway, at least for me, I didn't really know too much about engineering, but I was good at math, and I like science and physics and things like that. So I decided to just apply for electrical engineering when I applied to and see if I liked it. And right from the very first few weeks, I got involved in a robotics project in the electrical engineering department, and I really liked that.
I've seen some of the work up there in robotics. It's quite interesting, way beyond the high schools, actually. All kinds. So, what was the subject of your PhD in Berkeley? Was it robotics?
The subject of my PhD wasn't robotics. I was working in an area that's for microfabricated devices, so things that have features that are on the microscopic level. And the particular project that I was working on was being able to move around cells, like your blood cells or things like that, so that you could be able to sort between different types of cells, like a cancerous cell and a healthy cell, or a live cell and a dead cell, or things like that.
You mean with little devices, little robot devices?
Something like that, yeah. Little structures, microscopic structures, because the cells themselves are microscopic. So in order to be able to move those around, we need to make tiny structures that are around the same size.
I saw a movie about this once.
Yeah.
It was a long time ago.
Oh, the Fantastic Voyage.
That's the one.
Yeah,
Fantastic Voyage.
Yeah, so we're not at that level yet, but kind of along those lines, where we're trying to make structures that are about the same size as cells, so that we can work with them and do medical procedures that aren't possible any other way.
Wow. So is this something you're just holding in your back pocket now, or are you working on this as we speak?
No, so I'm still continuing to do some work on that. So we're not here to talk about my work in that area.
We're here to introduce you, though.
Yeah, so, but one of
understand who you really
right. So one of my other research projects is in that area where we are using what we call a microrobotic system. So we're using these microstructures to move around cells, and the idea is that if you can position cells in the right locations relative to one another, different types of cells, then you can do things like build up an organ or a tissue outside of the body. And so maybe in the future, if our research goes the way we planned it, in the future, you can go to the doctor when you're healthy, you drop off a few cells, he puts them into our fancy system, and you start growing a bank of spare parts for yourself. And then when you get sick later on, you don't have to be put on an organ donor list or anything like that. You open up your freezer of your own spare parts, and there's no issues associated with that. You don't have to do like animal testing.
It's not going to reject.
It's not going to reject. Yeah, and you don't have to wait around it. It's already there.
You know, Aaron, we're having a program on August 27th at Laniakea down here, the Women's Y on Richard Street, a downtown forum program with Hawaii Pacific Health, with an executive vice president. Her name is Virginia Pressler, and half a dozen researchers from the medical school and from the cancer centers. There's two of them, actually. And they're going to talk about research in this level. I mean, I don't know if they're going to talk about the engineering aspect, but the latest research going on in Hawaii today, and I urge you to come to that.
Okay.
If you go to the thinktechhawaii.com, you can sign up for it.
Okay, thank you.
You too, John.
Yeah.
Okay, let's turn to John. So how did you decide? Why did you decide to go into engineering? Was it a voice that came down to you one day, or what? Or was it Aaron? Maybe he talked to you.
Well, when I was young, my dad would a lot of times bring home a lot of broken spare parts that he would see off of the road, and then what he would do is he'd take them home and fix it up for the family. And so I was always interested in like tinkering and stuff like that. And then when I went into my undergraduate degree, I actually started off in civil engineering. But then a lot of my friends were in electrical engineering, and they had all these cool projects where it was robotics. So it was where they were doing a project called Micromouse, where they're programming.
I remember that, Micromouse. Yeah.
So they're programming this little. I guess it's completely autonomous, where you're not controlling it, but you're programming it so that it can smartly solve a maze. So what it wants to do is get to the center of the maze as quickly as possible.
In the engineering school.
Right, in the engineering
I saw
school.
this. I have footage of this. This is a couple of years ago, but yeah, okay.
So there wasn't anything like that for civil engineering at the time. So I was completely drawn towards that, and then that made me switch to electrical engineering. And then from there, I did actually a lot of programming. And then from there, another project that I was really interested in was a small satellite project, which are satellites that are about the size of a loaf of bread. And so it's called a CubeSat.
What's it called?
It's called a CubeSat, cube satellite.
CubeSat.
So it's I guess based off of small cubes, and then ours is a 3U. And so that satellite actually got launched recently, and so its job was to calibrate radar stations around the world. And then from there, so that project was under Dr. Wayne Shiroma, and he's the co-advisor with Dr. Ohta.
In your current project,
Right.
on liquid
metals.
metal circuits,
Right.
which we're going to get to in a minute. Yeah.
So now I'm in my first year of my master's degrees. I just finished that.
Okay. Exciting. You're really in it now. What's your career plan?
At first, I really wanted to get my PhD, but I think I want to get more experience in real world and then come back.
You mean
And
like a
then-
job?
Yeah, a job.
Like a job on the mainland or a job here?
I really, the more I travel, I really like to see the outside world, but only for a week before I want to get back home.
Listen, I get carried away about it. Good choice. Well, so when you say job, you mean research job or job in industry? Or
I
is it
think
the same thing?
a job in industry I would prefer, because there's a lot of, I'd say, interplay between research and industry, where you do research towards what maybe something industry is looking for, and some of that experience I think would be really valuable for.
So would you go out? This is an important question. Would you go out and take a job that wasn't in your line of work, so to speak, You know, you're working in certain projects now, you're invested in certain projects. So somebody on the mainland, for example, offers you a job in another engineering, another electrical engineering area. Would you take that, or would you insist on, you know, continuing the track of your examination?
I think it really depends on
Money.
an engineer's situation. Like in my undergraduate degree, I started on more of the computer engineering side of things, where I did a lot of programming. But then I was really interested in on the hardware side of doing stuff more hands-on, which is kind of the stuff I'm doing now. And so it really depends on your interests, how far you're willing to go, I guess. Depends on where this job is and stuff like that.
Yeah,
But
sure. But it reminds me of one of our directors here at ThinkTech is a biomedical engineer. She went to UH, but then she took a graduate degree on the mainland. And they offered her a job at Pearl Harbor in nuclear engineering.
Mm-hmm.
Which is not all that close to biomedical engineering, but it's engineering.
Right.
And it was a very exotic job, you know, nuclear, whoa.
Mm-hmm.
She took the job. There are not that many engineering jobs out there in Hawaii.
Right.
So, yeah.
So that's a choice that you know, some of our graduates have to make. They may not be doing something that's exactly the kinds of courses that they studied while they're at UH, but we try to teach them in a way that they're not stuck on doing something that they learned in a course. They can adapt and learn as they go. And you know, our graduates have been pretty successful at doing that kind of thing.
While I'm thinking of it, Aaron, let me pose an age-old adage to you.
Mm-hmm.
Is in every scientist there is an engineer. Or putting it the other way, in every engineer there is a potential scientist. And that you need one for the other. Am I right about that?
Yeah, I think it does go both ways because you know, as a scientist, when you're trying to find out new things or you know, advance knowledge, maybe in order to do an experiment or in order to find out a certain thing that you're looking for, you need some kind of technology that doesn't necessarily exist. And so you'll see, you know, scientists with the official title that are kind of rigging up these technology in order to meet the need that they have. Same thing for engineers. So we are, you know, especially with this project, we're looking more on the science side of things. So we're looking at engineering problems. In the case of the project that we'll be talking about, you know, how do you take what is normally a circuit that can't change, and how do you make it so that you can change it whenever you want to? And that involves looking at fundamental scientific principles.
I want that. And right after this break, we're gonna swim in liquid circuits. Okay, that's Professor Aaron Ohta, and master's candidate, PhD candidate? Master's candidate, Joanthan Dang. We'll be right back after this short break.
I'm Hong Jiang, host for Asia in Review on Tuesdays.
And I'm David Day, host for Asian Review on Thursdays. Both of us broadcast our respective shows at 4 p.m.
And my topics tend to deal with questions related to environment, culture, history, and sometimes human rights.
And my shows tend to be on international business, foreign policy, geopolitics, and national security. And you can watch our shows live on the ThinkTech website at thinktechhawaii.com.
And
Aloha, this is Keli'i Akina. It's my privilege to be the host of Hanakako, a weekly program on the ThinkTech Hawaii Broadcast Network. Hanakako, what does that mean? Well, many people have heard of Pule Kako, let's pray together. Hanakako means let's work together. Let's work together to build a better economy, government, and society. And every week, Monday from 2 to 3 o'clock, you will see movers and shakers and other people who are working together to build a better economy, government, and society. Again, I'm Keli'i Akina on the Hanakako weekly program on the ThinkTech Hawaii Broadcast Network. Aloha. See you here Mondays, 2 to 3.
Okay, we're back. We're live. We're here at ThinkTech Talks. We're on the SOEST show, the SOEST hour here on a given Monday from 1 to 2 always. And we're talking about liquid metal circuits in Hawaii. The special kind of liquid metal circuits that you can only have in Hawaii.
That's right.
With Professor Aaron Ohta and Joanthan Dang, both of the College of Engineering in Holmes Hall at UH Manoa, across the East-West Center. right? Okay. Okay, so asking to present, Professor Ohta, what is this project? You're the principal investigator. What is liquid metal circuitry in Hawaii?
Okay, so this is a project that is currently being funded by the National Science Foundation. So we have some federal research money coming in to help pay for this.
How much?
How much? We have about $350,000.
Okay, it'll take you somewhere.
Yeah, to fund this research. And what we are looking at is a different way of thinking about electrical circuits. So normally if you take apart, say, your computer or your cell phone or any other electronic device, you're going to see a bunch of black boxes on usually a green board. And that board will have wires all around and all these little components on it. And those wires on the green board are usually out of copper or aluminum or some other metal. And you can't change it once it's there. The engineers design it so that the wires are laid out in a certain way. But once you make the board, it doesn't change. But let's say you wanted your computer to behave in a certain way on one day, and let's say the next day you say, well, I don't really need my computer to, say, be video processing or something really processor heavy. You just want it to have a very long battery life. And so maybe you could accomplish that by moving around the metal on the circuit, but that's not possible right now. So what we're trying to do is say, okay, well, all of these circuits so far have been designed assuming that the metal is solid. You can't move it around. But what if you use a liquid metal, and now you can move around the metals, you can change the circuits, make them much more efficient or better suited to particular applications when you need them. And that's the basic idea behind the project that we're working on.
And how do you actually move them around, though?
So there's a bunch of ways that you can move around these liquids. And you could just, if you think about the liquid metal like water or something like that, you could have a pump to move around water. So you can also use the pump to move around the liquids. Now, that's not necessarily the best way to move around things in an electronic circuit, because a pump is mechanical, and you don't want to add a mechanical thing to an electrical circuit. So what we're exploring are electrical ways to actually move around these liquid metals. So you use the same kind of electronics that are already there for your circuit, and you use that to be able to move around the liquid metal, and you can say, okay, well, I want to change this circuit to do this kind of performance at this time. You flip a switch, it sends an electrical signal, and it moves the liquid metal to do it that way.
Okay, two questions before we move on to Joanthan Dang for his contribution to this project. One is the changes are by electromagnetic forces then. The metal presumably responds to magnetism.
It depends on the metal. The one we're using is not magnetic.
Oh, is that?
Yeah.
So how do you move it around then?
So we just use a voltage to move it around. And so what the voltage is actually doing is it's adjusting the surface tension of the liquid. And as you know, surface tension, that's what makes if you fill up a glass of water, what makes the water rounded.
Yeah, right.
It's what makes water droplets form into a sphere. It's not that significant at our sizes. Like, if you have water, when you touch it, you don't really care about the surface tension. But as you make things smaller and smaller, like they are in electronics, that surface tension force becomes much more significant. And so you can use that to actually move things around.
So you can change at a microscopic level, I guess, or a very small level. Instead of the wire going to the left, it goes to the right.
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 Okay, and the other thing is, and it just dawns on me, kind of in a free float of imagination, is you could have a smart version of this, which says, this computer is not as efficient as I want it to be, and I think that if I played with this a little and moved a little over here and moved a little over there, it would be more efficient. I'm going to try that, trial and error, and if I find, I being the computer, if I find that it is more efficient putting it over here instead of there, then I'll leave it that way. And so tomorrow I'll be a better computer for you, Dad.
Right. Yeah.
Can
yeah.
do that?
Yeah.
Right.
So that's definitely a possibility using this kind of technology. I mean, the field is really wide open. There's a lot of things that we think you can do with this, with being able to move around and control these liquid metals. Because it's so wide open, we're choosing right now to focus on a little bit more specific kinds of applications, but that would be something that could be possible. In the
So
future.
are there others working in this field?
There are a few other groups. Worldwide, there's probably about 3 or 4 other groups that are kind of playing around with liquid metals, although it is becoming more and more popular as time goes on.
And you're in touch with all of them?
Yeah, we. Right now, like I said, it's kind of a small field, so everyone kind of.
But, I
knows
mean, are you
it.
collaborating? Are you sharing findings? Are you sharing, progress?
Not collaborating right now, although we have talked to some other groups about doing some work together.
Okay. Well, let's turn to John. John, you have pictures, and you have a microphone too.
Right.
Can you give us through the pictures and like a verbal picture also?
Okay.
What your work is and how you're contributing to this project?
So if we go to the slides, so one of the most well-known liquid metals is mercury. And
Okay.
so
So
mercury.
we have a slide now of liquid metal. Is that mercury? we
So
talked
this
about?
is gallium, which is the liquid metal that we're working with. But to introduce the subject, one of the ones that most people know is called mercury. But the reason why research hasn't been focused on mercury is because it's highly toxic. And so recently there's a mixture of metals called gallium. So it's gallium based, and it's a mixture of gallium, indium, and tin. And in a certain ratio, it's able to melt at a temperature of less than -19 degrees Celsius. And so that is how we're using, that's the liquid metal that we're using for all of the devices that we'll be talking about.
How cold is that?
-19 degrees Celsius. So water freezes at 0 degrees Celsius, and room temperature is about 25 degrees Celsius.
Okay, so this melts at -19 Celsius?
Right.
So below the freezing temperature.
Below the freezing, it's liquid.
Yeah.
Oh, that's interesting. You don't find that very often, eh?
Right. Right.
Okay, all right.
And so it's actually used for medical purposes. So it's in thermometers. Instead of mercury, you'll find gallium in thermometers, for example.
Gallinston. Spell it? Gallinstan?
Right.
Okay, Gallinston. Make a note.
So with this liquid metal, like Aaron said, that in the past, a lot of researchers, and so us too, we've used pumps. But currently, we've been looking at electrical actuation techniques. And so what we're doing is we're manipulating the surface tension of the liquid. And the surface tension of the liquid is directly related to the potential of the metal with respect to the electrolyte. So
Do you have a picture of this? You want to show the picture?
yeah, I have a picture. So for example,
Okay, there
in
it
this
is.
video here,
Okay.
well, in this picture here, what I'm showing is a slot antenna. And so what we have is the gray shiny part in the middle is the liquid metal. And that's in a solution of about 1% sodium hydroxide. And with those probes, I'm applying a voltage. It's a low actuation voltage, and it's low power. And then what it does is it moves the liquid metal from the left side to, diagonally down towards the right side. And so what those chambers there, well, the reason why there's those, we call it kind of like a caterpillar shape. What each of those interlocking chambers does is it gives the liquid metal a area that has what we call low surface energy. And what all liquids want to do is they want to minimize their surface energy. And that's kind of related to the surface area and volume of the liquid.
This is the surface tension issue that Aaron was talking about.
Right.
Okay.
So the reason why liquids ball up into a sphere is because a sphere is the minimum surface area to volume ratio.
This doesn't sound like electrical engineering. It sounds like physics.
It does play off a lot of physics and chemistry.
Yeah.
And
That's
so-
why electrical engineers have to take physics.
That's
too.
why it's a great subject. You bring all this into electrical engineering.
And then, so what each of those circular locations does is it gives the liquid metal a place for it to flow into after the voltage is released. And that way we can control, with a high degree of fidelity, where it's going to be. And that way we can control the performance of the circuit.
So what do you actually control when you do this? I mean, I can't talk this language, but there's got to be a certain measurement of the electrical energy flowing through.
Right.
And what are you controlling when you start making these changes?
So a lot of the devices that we've created are in the field of microwaves. And so that has to do with signals that are at very high frequencies. So the signals that your cell phone uses to communicate, and in a way even computers are when they're in the gigahertz, they're very high frequency signals.
Yeah.
And so at those frequencies, the signal, it's related to the wavelength of the signal. And so when the wavelength of the signal becomes an appreciable size with the circuits, then we have to, the dimensions of the circuits are incredibly sensitive towards the performance of the device. So for example, in the device I showed, it was a slot antenna. And so what it does is it doesn't radiate signals at all frequencies. It wants to send and transmit signals at a specific frequency that we say it's resonant to. And so that frequency is directly related to the size of the aperture of the slot. And so by moving the liquid metal, we're changing the size of that slot. And then with what we do is we take a measurement to show what frequency it's resonant at, and we also do a radiation pattern measurement to show where the signal is going and at what strength it's going.
So if I have liquid metal moving like this, am I vulnerable to shock? Am I vulnerable to, I'm thinking what you were talking about, phones
Right.
and computers, giving them a whole new dimension, really, of possibility. But if I hit the computer on the table, drop the phone, is that going to affect the liquidity aspect? Is that going to also have an effect on the way the frequency goes, or the way the electrical energy is passed through the material, or does it not matter?
It definitely does matter. So it depends on the size of the liquid. And so you could think of, if you had a bucket of water, of course when you hit it, it's going to spill some water out. But when you go down towards microscale, the liquid becomes much more resistive to you just dropping your phone.
Because of surface tension.
Because of
and other forces.
Yeah, other forces as
Yeah.
well.
Back to physics. Yeah.
Right.
Right. And then what you mentioned about touching it, well, so galvanizing is non-toxic, but it does. But touching circuits does affect its performance. And if people have heard about the iPhone antenna gate problem for the iPhone 4, where they're being told that they're holding it a wrong way, and then that would affect the performance of the signal. Of people couldn't call people and couldn't receive signal and stuff like that.
Okay, so what are your experiments like? I mean, you're experimenting with the Galstan, you're experimenting with putting it through, changing the effective size of that slot, and you're looking at the result and how you can manipulate the result.
Right. So
Are you using it in a practical sense too for a device? Have you gotten to that stage?
we're not at the point of actually integrating it into a commercial product, but what we're doing is we're demonstrating the capabilities of the liquid metal. So the slot antenna was one example of an antenna, and then we've also worked with filters, which are just going through a circuit of passing certain frequency signals or rejecting certain frequency signals. So we've done a couple of different filters.
Show us some more pictures. We only have a few minutes left. I'm going to have the benefit of your artistic ability.
Like, so if we look towards the slide, so this is an example of a defective ground structure. And so for this circuit, there's a straight trace on the top that transmits the signal, but on the ground side of the ground plane of the copper, there's all of these etchings. And what we're doing is we're filling in liquid metal in certain areas to affect the frequency response of it.
So that's a filter. So you could use that to get rid of signals that you don't want and pass the signals that you do want.
Right.
So where do you get the metal to fill it in? Is the one on the top all filled in, or
So-
the one on the bottom all filled in?
So the one at the top is all empty,
Okay.
and then in the one below that, there's the center one is filled with Galveston. And then
Where did it come from? Did you have to?
the three? So
you
this
had
is
to actually apply it yourself.
yeah. This one was an example of using a pump.
Okay. Now, if it was out in the field for an actual device, would you do this kind of thing? Would you actually take Galveston and put it on and fill in the puka?
Well,
A Galveston puka.
yeah, you wouldn't really do that. You wouldn't do it physically yourself, but there are
Devices.
there are pumps that are integratable.
Tiny.
Right,
Tiny.
small pumps, but we're trying to move away from that, and so that's what
Right,
the
as you
example of the
mentioned.
slot antenna.
Yeah, okay. More pictures.
So all of these devices that John are showing are kind of the very first prototypes. We're right at the edge of science and engineering. So we're more showing if it's possible, not necessarily trying to make it a flashy package or anything.
Right.
Yeah, no, but this is great. This is real science now. It's more than, just electrical engineering for sure. You're incorporating multidisciplinary rules here.
Right.
You're pushing against. This is right at the edge, I think. Yeah. So I mean, you don't even know the effect it could have yet.
Right.
Right.
So where's your microphone? So let's go. We have about 10 minutes left, a little less than that. I'd like to go where you think this might lead. I mean, you guys are passionate about this, and like part of the reason is science, and it's cutting edge science. But you must have in your mind where it would actually change our lives. Why do we care? Why would this change our lives? You must think about that, don't
Right.
you? Yeah.
So we actually have another slide to show this.
Okay, please.
So on the left is the United States frequency allocation, and so that shows all of the frequency channels that people are allowed to communicate on. And so,
It's very colorful.
right, there's tons of different frequency channels, communication channels, and so what we're trying to do with liquid metal is that a lot of times you'll be in a certain environment where there will be too many people on one frequency channel, for example. And so, like maybe you're at Aloha Stadium and there's a bunch of people in one location all on their cell phones. And so that's what we would call a frequency spectrum congestion, where there's a lot of people. And so by being able to switch to other frequency channels, you're able to better communicate, to have more people talking. And so what we want to do is we want to be able to integrate these liquid metal reconfigurable circuits and create electronics that can adapt to these varying demands and changes.
But if you came to me cold and said, look, we got congestion over here, this area, I would say, well, the machine can tell there's a lot of congestion in that area of the band. So we're going to have it go over just a little bit. And it's going to telegraph that to other people on that network. And so now we're going to be just an inch away on another band. But you could do that with existing technology. I guess they do, no? Why do you need this liquid metal circuitry to do that?
You can somewhat do it with existing technology, but our way has the potential to be better.
Faster?
Faster. Also, you can get a higher quality communication channel.
More accurate, right in the right
Right.
place on the band.
Right.
Right.
So the way that you can switch frequencies now is you have an antenna that works okay for a lot of different frequencies, but it doesn't work really well at whatever particular frequency it's working at a given time. And then you have some filters there to just try to get rid of all the noise. But we can, sculpt a antenna that is really good at the particular frequency you need at that time. And then if you need a different frequency, we'll reform it into a very good antenna at a different frequency.
Antenna meaning a really tiny little antenna.
Right, yeah, like an
Okay.
antenna that would be in your
cell phone. Yeah,
Right.
okay. You're a man of nanotechnology, Aaron. I know you are. Think small.
Right.
So what else? Is there anything else that comes to mind where this might actually, change the world and be disruptive?
So it's not only with microwave circuits. Liquid metal also has a very high thermal conductivity, so it can transfer heats. So there is potential for it to be used as maybe as a pump itself to transfer away heat. And in addition to that, there's other things that we're looking into towards maybe using it as a way to transfer mass, because liquid metal has a high density, and so that could be related towards maybe energy harvesters, where where devices where there's a certain frequency of motion, like maybe you're walking at a certain motion at a certain pace, and then you want to be able to harvest that energy. You have to be able to tune a device so that it can match that pace, for example.
I may be way off, and I'm certainly not an engineer or scientist, but it struck me that this might be a key to making more efficient batteries, conceivably. In handling energy movement within the battery, or fuel cells. Ooh, you want to borrow my pencil? Well, I guess the point is, you could think of all kinds of things that
Right.
conceivably could benefit by that fine-tuning ability
Right.
to come right in on the dime and be exactly where you want to be.
Right, right.
With motionless, without any moving parts, essentially. Like little pumps, you don't need that.
Right.
And doing it at a very nanotech level and doing it sort of ubiquitously in a larger device. Ooh. See, this could change the way that all those devices work.
Yeah.
you know.
So the idea is for the end consumer, they're not going to know that their device is actually using liquid metal, but they'll just see an improved performance or an increase in the number of situations where they can use their device and how well it performs.
Now, you mentioned at the outset, Aaron, that this was all about Galveston. And or you did actually, John. Somebody did. One of you guys. I know one of you guys.
Right.
Yeah, John did.
And it's a combination of three metals.
Right.
And somebody has to actually make the three, make them into one metal.
Right.
Okay. Why Galveston? Why those three metals? Why those three proportions? Could it be that another combination of metals would work better? And is anybody working on that?
Well, so the answer to, I guess, the first part is that, so Galveston is what is called a eutectic mixture. So it's the best, or it's the lowest melting point for those three metals.
That's what you want to achieve, the lowest melting point. But if I gave you another combination that gave you a lower, below, what is it, minus 19 Celsius,
Right.
then you would say, good job, Jay, we'll take that one instead. Right?
So
Yes.
yeah, so well, it's not only the melting point, but there's also the electroconductivity of it. So how good of a conductor of signals is it? And then also maybe you want to be able to reach very high temperatures before it turns into a gas. That's another possible issue. But metals usually take very high temperatures before they turn into gas.
Yeah.
So that's not really an issue.
So where is this going to go? I mean, how far into the project are you now? How long is it going to take to finish at least, the steps that you see right now? And what follows this project in terms of advancing the science? Thoughts?
So we've been working on this project for about 3 years now. We've gotten to the point where we have some of the science behind how we're going to move and manipulate this metal down. We still need to refine a little bit on that and really explore the limits, like how small can we actually go, how fast can we move around these metals, what's the limit on the types of shapes that we can make from it, for example. And then At the same time, we're also pushing towards making it into a more commercial type device. So from all those like proof of concept prototype kind of pictures that John showed, something that's a little bit more packaged to something that would be a consumer product.
I also get the idea that with this kind of technology, I mean, as it seems to be, you could make smaller devices, smaller circuitry. Am I right about that? You wouldn't need so much circuitry or such a size. You could go smaller, and if you could go smaller, then we really could have Dick Tracy and cell phones on your wristwatch. Am I right?
Right.
Is that where this is going?
Yeah, because like for example, in a cell phone, they have a filter bank, so you're switching between different filters in order to try to get the frequency that you want. But if you just replace it with one filter that can change itself, then you're saving space there already.
And every piece of space is critical.
Right. Yeah, because it's not only filters, but also antennas and amplifiers, and it's a long chain of different devices that are tuned for certain frequencies. And so what liquid metal offers is the ability to capture hopefully all of those capabilities into one circuit that's able to adapt and then change to whichever one that you would want at the time.
This is really where the cutting edge is, isn't it? I mean, you could change electrical engineering with this. I mean, this has implications in all of electrical engineering. Am I right?
That's what we're hoping.
Yeah, exciting. Well, when you win the Nobel Prize or whatever, I hope you'll still talk to me. So after the existing grant is spent, what happens then? You go back to the well for another more significant grant and continue the research.
Right.
How do you do that?
So
they want to know because they want to emulate exactly what you're doing here.
So we're trying to get more money out of the National Science Foundation. We're also contacting partners in industry that typically work with UH and especially our department and the College of Engineering as well, so that we can get some company perspective for when we're pushing towards commercial products.
David Lasner spoke to us last Thursday. You remember him? And he talked about the Office of Technology Transfer. He talked about getting patents. He talked about trying to protect intellectual property at the university. So I hope that you fall in that zone one day soon. I don't imagine you have any patents yet, but it's out there.
Yeah, we have provisional patents on the technology.
Good. Okay. Well, I hope you guys come back and talk to us as it goes forward.
Yep.
All right, and you stick with it for a long time, and you change the world. Why not? That's why I titled the show "Liquid Medical Circuits in Hawaii."
In Hawaii.
It should be, like the Aloha Protocol and the Internet. It should come from here.
Yeah.
That's Professor Aaron Ohta and Joanthan Dang, both of the College of Engineering. And this is ThinkTech Hawaii, ThinkTech Talks. You're technically on the SOWEST show, but today I guess you could say it's the engineering show. Thank you, gentlemen.
Thank you.
Aloha.